within valence bond theory, we often use the terms sigma and pi to describe orbitals and or bonds, and although a real good technical definition of sigma and pi is not within the domain of an introductory organic class, it's more a physical chemistry type of idea, we certainly want to look and explore what sigma bonds and pi bonds look like and where they come from. So sigma is the Greek letter S, and it essentially within this domain means S-like, or S-esque, you might say. And pi bonds, pi is again Greek P, you might say, and this would be, you have P-like, or similar to P orbitals interacting. And I'll try to show in what way are the sigma S-like and the pi P-like. And the first one would be just simply, if you had an s orbital that approaches another s orbital and overlaps with it, you get a certain area of interaction and an orbital. And so if you had, again, valence bond theory says that orbitals overlap to form bonds. So if you had, say, a 2s orbital interacting with a 2s orbital, they'd interact like that and you'd get a bond. Now if you had two p orbitals, but they were oriented in this fashion, right, the area of overlap between these two p orbitals would look exactly like the area of overlap between those two s orbitals. And the way I'd often try to describe the similarities is just by covering up everything except the area of interaction. So you could see that this orbital overlap and this orbital overlap look identical in the area of overlap, so there's similar bonds being formed from similar overlaps. And it doesn't matter that the source orbitals in one case were s orbitals, and in the other case might have been, say, 3p orbitals. If they're overlapping in this head-to-head, in line with the internuclear axis kind of way, then they're going to form sigma bonds. So the sigma bonds look like this. You can also have a hybrid orbital, like an sp orbital, or an sp2 hybrid orbital, or an sp3 hybrid orbital, interact with another hybrid orbital. And if those guys overlap in a head-to-head fashion like this, then you have a sigma orbital. So it's all about what the orbital overlap looks like in the area where the orbitals are overlapping. And I could continue on with this. They don't have to be along this line. I could do an internuclear axis this way. I could do something totally crazy, like take a d orbital and interact that with a hybrid orbital. So say an sp3 with a dz squared, and it doesn't really matter what the parent orbitals are if the interaction between the orbitals looks like that. So if the interaction is just a single interaction along the internuclear axis, so you can see where the atom nuclei would be, that's a sigma orbital or S-like. And one that you'll see quite a bit is a hybrid orbital, like an sp, interacting with an s orbital, and that again is a sigma interaction. So any two orbitals interacting head-to-head in this fashion is going to be a sigma overlap between sigma orbitals and form a sigma bond. So these are all little sketches of sigma bonds. Now how do you get a pi overlap? Now a pi overlap comes from a double interaction between orbitals. And when we draw these p orbitals, we normally draw them too skinny and long compared to what the real wave function looks like, and that can be misleading. But if you have a p orbital on one atom, and it gets close to the p orbital on another atom, then you have this interaction that rather than right between the nuclei, like here, if you look at where the nuclei are, along the internuclear axis you have this nice overlap. Now between the two nuclei there's nothing going on, but a double interaction above and below. So this is essentially one bond. This is a pi bond, which results from a p orbital interacting with a p orbital, and those guys are parallel. So you'd say this is a pi bond formed from parallel. So we get our geometry muscles flexed a little bit. The pi bond formed from parallel p orbitals. So if like this was the y-axis was vertical here, then this is a py on one atom interacting with a py on the other atom, and this double interaction forms one bond from the overlap of these two orbitals together. So that's the typical pi bond you'll see in organic chemistry all the time, is a p orbital that's parallel to another p orbital, and these are going to be the non-hybridized orbitals. So your hybrid orbitals are generally involved in sigma bonds. Your unhybridized p orbitals can get involved in pi bonds. And if you go on to some exciting inorganic chemistry, you might see a crazy d orbital saddling up next to a p orbital. And again, the result of this would be this double overlap that would result in a pi bond. So this would be a pi bond from a d and p orbitals. And I could put the geometric orientation of these, that if this is a dxy, then I believe that would interact with a py, and you'd get that type of interaction. So there's plenty of ways to get pi bonds, and they all result in when between the nuclei along the internuclear axis, there's nothing particularly going on, but there's this double interaction of the orbitals above and below the internuclear axis that result in the pi bond. And this is where, again, the area of overlap looks similar between these two situations, but very different from this one. So this you could clearly see as two s orbitals interacting. This looks just like two s orbitals interacting, even though it's really p orbitals. You can't get this interaction from s orbitals, because s orbitals are spheres, and you need these two lobes to interact at the same time with each other in order to get the pi or double interaction. So sigma bonds are going to be for single bonds, and pi bonds are going to be for multiple bonds. And you'll see that quite frequently, that these are going to be the multiple bonds, and these will be the single bonds. So the sigma framework is the single bond network that holds a molecule together, and then any additional bonds are going to come from the pi overlaps.